Welcome, this is an AQA A2 Physics Unit 4 video. This is the last, well, in terms of, probably not how I'm going to upload it, but in terms of the actual AQA book, if you were looking through that, this is the last topic, and it's the last part of the last topic of electromagnetic induction. Now, in the first part, I stated what electromagnetic induction actually was. And I talked about Faraday's law, and I talked about magnetic flux. The rate of change of magnetic flux was the EMF was directly proportional to the rate of change of magnetic flux. Now, in this second part, what I'm going to be going over is obviously what I've tried to draw here is the motor, an electric motor in. Obviously, we've got the north and south poles of a magnet here. These red lines are supposed to represent the field lines. This black bar is representing the magnet. Okay, and what I've done over here is I've extended it, sort of zoomed in, essentially. You know, the technical side of things on what where these angles actually are. So basically, it's to the horizontal, to the vertical here, and sort of to the almost horizontal. Okay, and I'm going to go into how that enables us to draw a certain graph, okay, and I'll be going on to explain EMF from that. We're going on to something called back EMF, which is actually a lot easier than it sounds and is related to this, okay. Then I'm going to be going on to Transformers. Now, not the movie. I'm not going to be flicking the movie on for those of you that like that kind of thing. I do apologise. Unfortunately, you'd have to pay to see that, and that means you'd pay to have to see one of my videos. And I'm pretty sure that would end up with the views being at minus 5,000. Basically, me paying myself to watch it 5,000 times. Okay, probably taking out a loan and being in debt. You know, it goes on. Okay, so anyway, that's pretty much what we're going to be doing. Within Transformers, I'll be just giving you a bit of a recap from GCSE, what you should already know. I know it's ages since you've done Transformers, especially if you're doing, you know, this is your second year, should be, unless you're incredibly smart. But you still got to be pretty smart to this new second year. Okay, so, right, so I'll be just recapping what you should know from GCSE, and then we're going to be building up a bit more into it. Stuff they didn't tell you at GCSE because you were too thick. I'm not going to round that up because that's essentially why they didn't tell you. Okay, so going back to this is what we're going to start off with. This should look familiar. As I said, it's an it's a magnet, okay? So we're going to, basically, these are field lines, and due to the forces we've explained before with the electric motor, this cuts through the field lines, okay, so it spins around, okay, as I said, I explained why that was, and a proper diagram on that in the other videos, in magnetic fields. Okay, so what we actually cut, when we cut through the field lines, we are inducing a current. It's essentially taking it out and dropping it in that coil thing we talked about in the first video for electromagnetic induction, okay. And we're inducing a current in here, an induced EMF, okay? So that's essentially what this is showing. This is showing the magnetic flux and the rate of change in magnetic flux, okay? So before we do too far ahead of ourselves, what this is showing is the magnetic flux, okay? And basically, the reason I've extended this bit here is these thetas can make up a triangle, okay? So if you imagine this, right, there's the hypotenuse here, and then we've got the right angle there. So in essence, we've got it as being here, okay? So hopefully you can imagine that, and this therefore is the hypotenuse of this angle, and what we want to work out is the horizontal and vertical component of the field lines. Okay, so in both contexts, we're going to be using the trig function cos, because we've got the hypotenuse and the adjacent, okay? And as this is representing magnetic flux cutting through the field lines, remember, therefore we have to use the cos graph to represent magnetic fields. Now, let's just assume we're taking things, taking the range between 0 and 2 pi, okay? So if our range is between 0 and 2 pi, okay, for cos theta. Now, I'm not going to go into the extremities of, 0.77 pi. Just going to do, okay, well, where is it in maximum, where is it in minimum, and where is it 0? Okay, so in essence, what we want to know, because this because the graph, I've kind of established, hopefully proven to you, that the graph for the for the magnetic flux, okay, so the magnetic flux, or total magnetic flux, is represented by the cosine graph. Okay, so as I said, hopefully I've kind of explained that to you. Alright, so if you were to work out where it's a maximum, okay, you would find out, this is just by putting the calculator and using the CAS diagram, okay, you would find it is a maximum at at pi and 2 pi, okay, so I've done my calculator somewhere, there we are, okay, so just to go over that for you, so make sure your calculator's in radian mode, obviously, okay, so cos of pi is -1, okay, so it's a minimum -1 at pi, therefore it's a maximum +1 at 2 pi. And why are we caring about this? Well, this cos graph is going to show the magnetic flux. So if you remember back when we were talking about magnetic flux in the first video, we said n phi, which is the total magnetic flux, is equal to BAN cos theta. And that's kind of, this is explaining why we have that cos theta attached, okay? Didn't explain it too well in the first video, but because we want the cos, because the cos theta is essentially how this is being put it into its horizontal and vertical components, okay? We apply it to this torque thing, to this total magnetic flux linkage, okay? So if the cos is positive, if the cos is a maximum, then the whole thing is going to be a maximum, because we can only either times it by +1 or -1 or somewhere in between. And the positive one and the negative one are going to give the most extreme answers, okay? So that is what happens here. Now, it is also at 0, so it's at 0 at pi on 2 and 3 pi on 2, okay? So that's where it is a 0, okay? So basically you can draw that, it's a standard cos graph, okay? So therefore, using this information, as I said, you probably should have already known what the cos graph looks like. Well, at 0, if you do cos 0, this is how I start by drawing the graphs, okay? It's at 1, so it's 1 here. The first intercept at 0 is pi on 2, and then it's 3 pi on 2, okay? So it looks something like that. Now, as I said, that's not perfectly accurate, but you get the idea, okay? So, what does this help us to understand? Now, that's very good. That shows us the magnetic flux linkage graph for this motor, okay? So it's just the magnetic flux linkage graph. Now, going back to Faraday's law says the rate of change of magnetic flux, the EMF is directly proportional to the rate of change. Now, it doesn't matter that it's directly proportional, well, obviously it does, but it just means it's times by a constant. We can almost rule that out, okay? Because I'm trying to get across to you that the EMF is directly proportional to the rate of change of magnetic flux. Now, the rate of change of magnetic flux is the gradient, okay? The rate of change, that's what we mean by dy dx, is the rate of change, just the rate of change of y with respect to x, okay? So it's the gradient of the graph, okay? Now we said the EMF is directly proportional to the rate of change of the flux linkage, which is what this is, okay? So therefore, the EMF graph is the graph which is the gradient of the flux linkage graph. And if you were to work out what graph this would be, okay, so remember the one on the top is for the flux linkage, I just put that flux linkage sign, and the graph therefore, which is the gradient of this graph, is the, so if you differentiate, you can either just draw the gradient of that graph, or you could just differentiate the cosine, sorry, to get sine, okay? So the EMF graph is a sine graph, okay? So it's the sine theta graph. You could just simply draw that between 0 and 2 pi, okay? That is the graph of the EMF, or induced EMF in this case, Okay, so hopefully you've been able to understand that, really. It's just recalling an old knowledge and applying it to this case. Okay, so what we're going to talk about now is this thing called back EMF. Now, I'm not going to draw anything particularly new on this on the whiteboard, and that's because we're just going to be applying this knowledge of this motor. Okay, so your standard equation for EMF is E is equal to I big R plus I little r. And you know, I big R is equal to the potential difference, so E is equal to V plus I little r being the internal resistance. Okay, so why am I mentioning this? Well, it's obviously back EMF, so it's going to have something to do with the EMF equation that we learned back in first year, okay? Now, back EMF just kind of goes over the induced EMF that is caused by the motor here. Okay, and essentially, I'll read it out for you. The faster this motor spins, the more current is being induced because the more electrons are being moved out of the way, which is increases the amount of eddy current, which is just the current. The eddy current is just the induced. It's just the name for the current which is induced by the electromagnetic induction. Okay. So the faster this spins, the more induced current is created, and basically all this energy is being created. Well, not created, that's the wrong word. All this energy is being put into this system. Okay. So the only way we run energy over change of time is power. So we have to relate some kind of power equation to this. Okay. Now the only way we can turn this into some kind of power equation. Okay. As I said, you could probably best leave it as this actually. The first equation, doesn't matter if you leave it as the second equation, doesn't really matter. Okay, so we times all of the equation by I. Okay, so if we were to carry on with this, it'd be IE is equal to IV plus I little r. I squared little r, sorry. Okay, so what does this tell us? Well, if we put this in word format, okay, that the power, power transferred to the mechanical, because this is induced EMF, it's to do with the obviously the EMF. So we look at this, okay? So it's the power induced, because when there's no internal resistance, the EMF is equal to the potential difference. Okay, so that's the same as IB, really. Okay, so it's basically the power transferred to the mechanical. Power transferred to mechanical power is equal to, sorry, I'm just trying to relate this, to power supplied by the source plus power wasted due to resistance. Now if you wanted to rearrange that, you'd say the power wasted due to resistance is equal to the power supplied by the source, take the power transferred to mechanical power. So for that last one where I said power is wasted due to resistance, is equal to power supplied by the source, take power transferred to mechanical power. It's just this rearranged, okay, to say I squared big R, or in this case IV, okay, is equal to I little r. Sorry, now I've made a bit of a mess there. Right, I do apologise, but hopefully you've got what all of them terms mean. And that last little point where it says power is wasted due to resistance is equal to power supplied by the source, take power transferred to mechanical power. That's the key bit of information you needed to get. Now, as I said, as long as you understand that, and it's just a rearrangement of one of these, I think I made a bit of a mess in. The calculation isn't wrong, but I think I've just got my signs middled up, okay? But that equation where I said the power wasted due to resistance is equal to power supplied by the source, take the power transferred to mechanical power, that is correct. You need to be able to understand that statement. Okay, so that's really magnetic flux. Now we're going to apply this to transformers. Now they wouldn't have mentioned it, as I said, in GCSE, because I'm pretty sure if you were sat in your GCSE lessons and your teacher walked in and said, right class, today we're going to start talking about magnetic flux, you would have got out of that class, physics class or science class, and gone, right, I'm going to kill me some zombies on Call of Duty. And suddenly you've become, you know, completely unable to speak any correct English, but basically what I'm trying to say, you might not have liked it so much. Okay, so this is what we're going to talk about now. So I'm just going to draw kind of a basic sketch, really, of a transformer. But I'm going to add some things, well, not add some things, it's just writing on the word magnetic flux. Okay, so this is some kind of typical transformer that you might see. Now, I did debate just then whether to pause the video, and just come back with it fully drawn, but I'm kind of sick of walking backwards and forwards. Okay, so hopefully you get the idea. Transformer looks like this, and in this part of the video, I can actually talk through it. I'm just going to demonstrate why we need an alternative. Just to recap what you should know about transformers, and go on to add some extra things about why. I come up with some extra equations that you might not have known before, recap a few old ones, and two certainties, kind of what transformers do, and then how we can increase the efficiency. And that's kind of the A-level thing, the efficiency, really, as well as a few equations. Okay, so just draw a few more coils on the primary. Okay, secondary, doesn't really matter, I'm just doing that. Okay. And going through the core is I'm just going to write on it the magnetic flux, okay? And just put primary, secondary. Now, so there's a proper, sorry. Okay, now we've got more coils on the primary, so therefore it is a step down transformer. I do apologise, because we've got less coils on the secondary, so the voltage is reduced. Okay, so that's what you would have been taught at GCSE. And also you would have been taught that it must have a alternating current, otherwise this won't work, it won't step up the voltage or step down. As I said, you weren't told why, but we're going to go into that. Another thing you would have been told is about that step up and step down business. Okay, so what we're going to do in this video is just go over why we need an why we must have an alternating. Oh, sorry. Another thing that you would have been told is we have a soft iron core, so it can be magnetised and demagnetized quickly. And I think that's, just thinking. No, that's it. Yeah, definitely. Okay, so that's what you hopefully should know. Now I'm just going to throw a few equations at you here. So the voltage in the secondary is equal to the number of turns in the secondary times phi, which we know is the magnetic flux times the area, okay, over delta t, change in time. And you could do that for the primary, so voltage of the primary is equal to the number of turns on the primary times the magnetic flux density, which is going to be it's going to be the same for both because we've got the same core, okay, over delta t. Right, so they're just two new equations, and it really just comes from obviously the magnetic flux density. So we just need to understand them. Really just imply BA to be theta to this phi business, okay, which kind of looks, due to my poor drawing, is looks like theta, but it isn't. It's phi. Okay. So one of the other equations that we introduce, as I said, I didn't say you did it in your GCSE because you might not have done. Okay, is this efficiency business, and that's quite a favourable topic at A level. Okay, so basically it's the power supplied, power supplied put into it over the power supplied that comes out of it times 100. So the power, I'm just going to label that as IV or VI, doesn't matter which way you do it. So it's I the secondary times the voltage of the secondary, or just the power of the secondary, okay, over the current of the primary times the current of the the voltage of the primary times 100, and that gets you your efficiency. Okay, and now if that's 100%, then IS VS over IP VP equals 1. So if we assume it's 100% efficient, then IS VS, okay, is equal to IP VP. Okay, So that's if it's 100% efficient. Now, if it doesn't tell you what efficiency it is, just generally assume it not. If we don't know it's 100%, then we just work out, well, this is what it would be, you know, if we know the current of the primary, the current of the secondary, the voltage of the secondary, but we want to work out the voltage of the primary, and we're told, for example, it's 88% efficient, this is just an example, what you would do is work out the voltage, what it would be if it was 100% efficient, plug it into that. Obviously it would come out to be 100% efficient, but then you would rearrange it to make it 88% efficient, okay? So hopefully that kind of makes some sense. Okay, so as I said, that's just a little bit of a background, really. So, that's just an extension from what you would have understood at GCSE. Now we're going to go on to the maximum sort of weighting on a paper that they would ask you about transformers. Okay, so the main thing obviously, because the efficiency is a big part of this at A level, okay, and what we need to do is apply our understanding of electromagnetic induction to be able to work out how we can make this more efficient, okay, and one of the things we're going to be going on from is this eddy currents as well, okay, so just to recap, eddy currents is just the current that is created from electromagnetic induction. Okay, so as I said, there's a couple of things, and really how I've labelled it is how to reduce transformer energy losses and basically how these losses are created. Okay, so the first one sort of isn't such a loss really. Well, you wouldn't have understood it to be a loss. Okay, so the first one is this. They would have banged on at GCSE about this soft iron core, so it can be magnetised and demagnetized very quickly. But what the hell does that mean? You know, why would we want to magnetise it, demagnetise it so quickly? Who cares if it takes 5 hours or 5 seconds? I mean, obviously you're going to be waiting for your power sort of thing, but why is that so? You know, why is it such a bad thing that they harp on about it so much? But they can actually tell you why, because you know at GCSE they lie to you. As I understood, anyway. Okay, so the reason that it could be magnetised and demagnetized early is, remember we were talking about the magnetic flux is essentially cutting through the field lines. Now that's the sort of half-arse definition. The proper definition is you can go back a little bit, but really that's what we end up implying, okay? So if it's magnetised and demagnetized very quickly, it changes the magnetic field very quickly. So the induced current, the temporary electric field caused by this induced current intersects the magnetic field lines of the magnet very quickly, okay? So it creates the electricity very quickly, which obviously means it's less costly for the electricity companies because it's more efficient. It takes less time to produce this electricity, okay? So that's really why we have this soft iron core. Now the shape of the core as well, why don't they just draw it in a circle? Well, this creates the perfect magnetic field lines that can be intersected very quickly, kind of relates to the first argument, okay? The low resistance wires, so these copper wires that go around these coils, they're low resistance because if they were high resistance, obviously that would take away some of the power as well. But the energy, there would be a lot of heat energy held in these wires, and if there's a lot of heat energy, there's energy wasted, and if there's energy wasted, it's not as efficient, and if it's not as efficient, it costs the energy companies more money, okay? And obviously they don't want to lose any money at all, so that's kind of another big thing. Laminated core, now when you would have heard laminated stuff, what I want you to think, it's not laminated a sheet of paper, it's basically, say this is our one of these sides of the core, okay, and laminated, what we do is we just put a sheet of metal, sheet of plastic in sort of lined like that. Obviously it'd be perfect, but more perfect than that would be something like that, okay. And why do we do that? Well, I was talking about the build-up of these eddy currents because we're changing the magnetic field, inducing eddy currents in this iron core, okay? And these little eddy currents, these little electrons, try and get through. But these sheets of plastic are insulators, so they can't get through these insulators, okay? And if they can't get through the insulators, they can't build up any heat, so the iron core doesn't get hot, therefore, you know, we don't lose any energy to heat. So really that's the transformer version at A level. So just to recap, the things that we need to discuss, for the efficiency is the soft iron core, which says it can be magnetised and demagnetized quickly, which means you can cut through the electromagnetic field to the field lines very quickly, as we mentioned. Okay, so soft iron core, low resistance wires. We also mentioned about these laminated core, which is essentially what I was trying to show here, but very poorly, as you can tell. So it's a laminated core. And then we also mentioned about the shape, okay, which, you know, I can't really focus on that one too much. It's more the other ones, okay. So really, it's all about, you can see how that relates to electromagnetic induction. And as I said, these two equations are given to you, and it's just a case of learning them and understanding them. Now, one more thing, actually, I should have mentioned this before. I do apologise. Going back to that magnet right at the start. So if you remember, right at the start of this video, so if you want to write this equation down, and you can always relate it. Now, I said that n phi, or total flux linkage, is equal to BAN cos theta. Okay. Now, what is this theta? Okay. So we still write BAN. Now, this theta is equal to, if you remember, simple harmonic motion. Our theta was 2 pi ft. Okay. So in other words, it's the angular velocity times the time. So the fraction to 2 pi. The time over the time period, okay? So that's for the flux linkage, okay? Now for the EMF, we said that was the rate of change, okay? So if you look in your formula sheet, you get, I think it's E is equal to E0 sine theta, okay? Theta having the same effect, that's for the EMF. Okay. Now there is another EMF equation in your formula sheet. So these two equations I just forgot to mention, and I've just seen them on my notes. So I do apologise about not mentioning them before, but you can just go back to the start of this video and I've mentioned them there. So really that's what this video is about. I do apologise, it's been a little bit rushed, but what I'm going to try and do now is go through some Unit 4 past papers, because I've now officially reached the end of Unit 4, so all the videos should be coming online if they're not already. We're going to be moving on to Unit 5 next, and we're going to be looking at radioactivity, okay? Which again is quite a lot based on GCSE and building on from that, even though we're in the second year of A level. Because we didn't do radioactivity in the first year, we're kind of, obviously it's another level up. Okay, but we're going to begin by doing Rutherford scattering, which we're going to go into more detail than you obviously did at GCSE. Okay, so thanks for watching, and we'll see you then.